Well, we're now on homework 2.2D, and this one doesn't require MATLAB, but it does require you to take a look at some of the code we've been using to do the triangularization. This section is all about counting the cost, and we've defined cost so far as the number of floating point operations. That's not perfect. I need to remind you of that. There is such a thing as integer operations. They are much quicker than floating point operations, so we ignore them. But there's also storage, and there's interchanges and things like that that we should be counting, and we're not. But if we did a really good job, we would. For right now, we're going to continue with the floating point operations and take a look how we can find the cost of this particular set of code. That's the code that is used to do the triangularization, not the back substitution, but the triangularization. Part A is to develop a new formula. You remember at the beginning of the quarter, we were coming up with formulas for adding up integers from 1 to n. We also had one where we added up the cubes of integers from 1 to n. And now we're going to develop another formula to add up the squares of integers from 1 to n. So your job is just to go back to those same methods we did earlier in the quarter, use induction, and prove this formula is true. So for part B, we're going to count the cost of this particular set of code, which is our triangularization code. We're going to be developing sums each time we end up with 4s, and we're going to count every single time a floating point operation occurs. Okay, so let's go ahead to our hints and see how we'll do part A. Here's the formula we're trying to prove. So in our usual inductive sense, we either assume that the sum from 1 to n minus 1 works, and we're just trying to add the nth term, or you could go from n to n plus 1, but in this case it's easier to start from 1 to n. So step 1 becomes showing this formula is true if n is equal to 1. Well, that's as easy as it has been before. If you just put a 1 in there, you only have 1 squared, and if you put a 1 on the right, you can figure out what that is. So you do that part, that should be very, very quick. Step 2 is if you assume that the sum from 1 to m is true when m is equal to n minus 1, then it necessarily would be true for when m is equal to n. So basically just stepping it up one notch. Let's get you started on that. The way you get started on that is you come up with the formula for the sum from 1 to n minus 1. Well, you just go up here, and everywhere you see an n, you plug in an n minus 1 here and here and here. That corresponds to those 3 terms. Then you can simplify it. This one's kind of nice. N minus 1 plus 1 is just n. And 2n minus 2 plus 1 will end up being 2n minus 1, which we see over here. So this is a formula that we can assume to be true because we are assuming by induction that when m is equal to n minus 1, that we have a valid formula. So just add n squared to both sides of this equation. You add n squared to this side, you get the sum from 1 to n of I squared, and if you add n squared to this side, you're going to have to do a little bit of algebra. So I think you can probably work that okay. Let's go to part B. In part B, we're going to scrutinize this logic carefully. And as we recall, every time you have a for loop, you're going to be adding up floating point operations for all the code that is nested within that for loop. So we are going to assign a summation using the same indices we have in the for loop, using the sum sign. Now the next one is embedded within the for loop, so we have another sum, but it must be a sum within the outer sum. So I'm indenting that just to make the point that we are going to be including everything in this sum as elements within this outer sum. Now we have one division, which is a floating point operation, so we'll have to add one floating point at this point in time. And then we have yet another sum developing from this for loop. So we will develop a sum from j equals k to n corresponding to the indices that we have on the for loop. Inside that sum, we have 1, 2 floating point operations. So we will need to add two floating points inside that sum. The end is just going to move the indenting back. There's no sums, there's no additional floating point operations. It's just keeping track of our indenting. Therefore, when we apply our floating point count to this operation, we will have two floating point operations but indented in at the same level as the +1 was. That's all we have to do. Everything else just brings in the code for a landing, and we need to assemble these pieces to form a sum that we can then calculate. So here it is. Our total count is going to be this outer sum of absolutely everything else that's below it. What's below it? Well, we have this sum here, and we have these terms, a 1, a sum, and a 2. So the 1, sum, and a 2. And the sum is always adding up to floating point operations as it goes. So go ahead and evaluate that just like we did before. Take a look at your indices to make sure that you can factor out things that are constants within sums. That'll make it a lot easier, and see what you get. So when you're done with this, this should simplify into a cubic expression. If you don't get a cubic, you've done something wrong. So we'll come back next time and see how we did.